All right. Hello everyone. It is now 2 o'clock, so we are going to get started. I'm sure other folks are going to be rolling in. But would like to welcome everyone to today's Third Coast Water Seminar Series. My name is Tyler Steven. I am the Technical Program Manager at Current, the organization that is managing the organization of this series. And today we will be hearing from Dr. Paul Westerhoff on water reuse and semiconductor wastewater management. So really quick, just to lay the groundwork and provide a little bit of background about this series, Current, as well as the initiatives that Current is a part of. The goal of this seminar series is to elevate research that is being done in the Great Lakes and beyond, centered around transforming waste into wealth, specifically looking at wastewater and historically other historical waste streams. Current is a nonprofit based in Chicago, focused on water innovation. We were founded in 2016, so this is our 10-year anniversary. We've been working on our mission around water innovation for those 10 years. We have three primary goals. One is to grow the circular blue economy. Two is to accelerate water innovation, both looking at the research and development side, all the way through translation and marketing and end use side, as well as three, to solve pressing water challenges. So Current is the anchor organization behind the NSF, behind a NSF innovation engine called Great Lakes Renew. This was awarded in 2024, and we just finished our 2-year initial period. So Great Lakes Renew is focused around the recovery of valuable materials from waste streams, so specifically energy, nutrients, critical elements, and water. And we do this through many different ways and in order to do many different things. So one is we want to help spur the circular economy transition. Two is we want to help the invention and commercialization of selective separation technologies, specifically looking at things that selectively separate out contaminants of emergent concern, such as PFAS, critical minerals, as well as other nutrients. And then finally, we want to attract and retain water-intensive industries in the Great Lakes region. Great Lakes Renew has a region of service, has a initial 3-state region of service focused on Illinois, Ohio, and Wisconsin. And then we hope to expand that to include Minnesota, Indiana, and Michigan in the future. So as part of Great Lakes Renew, we support research and development as well as translation and commercialization initiatives and workforce and ecosystem development. But on the research and development side, which is kind of helps give background to this seminar series, we are funding several different projects around PFAS detection, critical minerals extraction, nutrient recovery, and much, much more. If you would like to learn more about Current or our Renew initiative, we would love for you to follow us on socials. If you scan that QR code, that'll take you to our website. And yeah, without further ado, I will be handing it off to Dr. Junhong Chen, who will be introducing today's speaker. A little bit of quick run of show for how today is going to work. So after Dr. Chen introduces Dr. Westerhoff, he will be providing a 40 to 45-minute presentation, and then we'll have time at the end for Q&A, about 10 to 15 minutes. So feel free to drop any questions you have as the seminar is going or at the end of the seminar into the Q&A box that we have. And without further ado, I'll pass it off to Junhong.
Thank you, Tyler. It is my great honor to introduce our speaker today, Dr. Paul Westerhoff, who is a Regents Professor and Fulton Chair of Environmental Engineering at Arizona State University. He has over 450 peer-reviewed publications related to water. He's the co-deputy director of the NSF Science and Technologies for Phosphorus Sustainability Center. which is NSF STC, and director of the Global Center for Water Technology. I know he was a former deputy director for NSF-funded engineering research center called NEWT. He's also one of the leaders in the NSF Futures engine. He's also involved in the DOE-funded Norway hub. So I think Paul is probably the only person I know who is involved in all these large-scale water efforts. So very impressive. Dr. Westerhoff has received numerous awards. I would just highlight a few of them. He was elected to the National Academy of Engineering in 2023. He also received the 2020 AP Black Award from AWWA and 2019 NWRI Clark Prize, 2013 Arcadis AESP Frontier in Research Award, and the 2006 Paul Bush Award. So with that brief introduction, I can highlight a lot of other things for the next hour, but I'll turn it to Dr. Paul Westerhoff for his presentation. So Paul, the floor is
Great.
yours.
Thanks, Tyler. Thanks, Junhong, for the introduction. So I'm going to go ahead and share, get this full screen. Could you give me a thumbs up, Tyler, if that looks good?
Yeah,
Assume
we can
so.
see it.
Great. Good. So, today I'm going to talk about semiconductors and wastewater. This is work a postdoc Junlei Wang and Arnold are working with me on with funding through our Global Center of Water Technology, which is funded by the state of Arizona, and lots of great partners. So here's an outline of what I'll kind of talk about, and it's really about thinking about this renaissance of manufacturing in the United States, and specifically related to more high-tech manufacturing. So I'll start with kind of a pretty broad, outline, and we'll narrow in, and we'll get to graphs and data as we go along. But I really, have thought a lot and think that, this overlooked commercial, industrial, institutional sector in the water community has been a little overshadowed, by, residential home, water conservation, even, in-home gray water reuse and things like that. But it's a large sector. And, it ranges, and a lot of cities don't exactly know what to put in here, but, it's somewhere around 30 to 40% of the municipal water sales go to, the CII sector. And the CII sector is getting more and more interested in on-site reuse for a number of reasons. Some companies have sustainability goals. Some of it is about cost. Some of it is about, increasing cost of disposing of things, potentially energy recovery. I'll talk a little bit about public perception, as well as, if you want to expand your facility, you might need to also grow the city's infrastructure, pipelines, sewers, things like that. So here reuse can allow growth in the CII sector without that infrastructure. And by keeping everything kind of on site, you have a more control maybe over prevention of regulated or future, chemical or pollution issues. So I'm going to really focus on this commercial industrial, in even more focus on the industrial part of this. And, when we look at the growth of different industrial sectors in the United States over the last 10 or 20 years, semiconductor and electronic component manufacturing is really growing disproportionate to other, manufacturing shown here in blue. So that's kind of the real motivation here to focus on semiconductors, but it's kind of true around these other electronic components, but other, whether it's high-end pharmaceutical manufacturing or other manufacturing that needs really high quality, water, rather than maybe some of the older, industries like, pulp and paper, for example, very different in terms of their water quality needs. So just a little bit about the use of water in fabs. Here's thinking about billions of liters in the upper left-hand corner, and you see United States, and this is really related to semiconductor fabs. And this is really only part of the semiconductor ecosystem that I'll talk about. But you can see the U.S. is in the top 5 in terms of the amount of water that's going into these industries. And fabs use a lot of water, in part because they need a lot of water to clean the wafers. And we'll talk a little bit about it, but a typical fab, can use, tens of thousands of equivalents of homes, but there's lots of small fabs that might use 100,000 gallons a day, but large fabs might be 5 to 10 million gallons of water a day. So, there's a lot of water that's being used, and for a lot of reasons, across the United States, these blue dots show the locations of fabs, and then the color is kind of the severity of droughts and other water-related, risks. And some of them are in Southern California and Arizona, West Texas, and other dry regions. And there's issues for that or reasons. Some fabs need dry air. Otherwise they have to dehumidify air. There's taxes, energy, power costs, lots of reasons to cite them, as well as an ecosystem of companies, because a fab by itself isn't going to work. They need this entire supply chain around them. So fabs use a lot of water, and there's a kind of a new one growing here in Arizona. So TSMC moved here a few years ago. They announced $100 billion kind of additional investments. They have at least one fab already operational, building 2 and 3, and plans to build many more. And around them then builds this ecosystem of supply chain. So they need to build and buy silica wafers. They need to make the chips, and then they need to package these chips onto the wafers. And you can see they picked part of Arizona, North Phoenix, that has a lot of desert around it, a lot of growth. There's not a lot of trees. There's not a lot of rivers, right? So, as a consequence, you can find newspaper articles about water guzzling chip makers in Arizona, but even in a place that you don't think of as droughts, but even in Taiwan over the last few years, they've had water issues associated to the amount of water that's available. So I think this is where we come in and think about how to reclaim and reuse as much of the wastewater in fabs as possible. And so this is how these high-tech industries of the future, are and will grow in areas of water stress. And again, for other reasons, maybe not in, thinking about it only in water-stressed areas, but again, to reduce energy, infrastructure, and to meet their sustainability goals. This is going to be a trend that moves forward, I think, globally. So hopefully that's a little motivation. Why focus on industrial wastewater? Why focus on semiconductor manufacturing? Now let's go a little bit more into fabs. We think about semiconductor fabrication as like making the chip, right? But they make the chip, but then they have to put it on silica wafers. All those things come from upstream impacts of mining and refining that use water. I'm going to talk about this kind of manufacturing, packaging part. But of course, the chips are used in places like data centers that make us, happy with ChatGPT and other things. But these data centers also use water downstream. So I'm just really focusing in on, this water component in the manufacturing and packaging sectors. So when you look up, chemical use, across these, there's lots of different chemicals. You can see the higher volume ones used on the bottom. And it's not just one process, but there's kind of, solvents and chemicals used in stripping, photolithography, etching, wafer grinding, wafer cleaning. And the x-axis here is lower to larger wastewater volumes. So this chemical mechanical planarization, they need high quality water that they put chemicals in, and they do this between each kind of iterative kind of growth in here of the chips, which may have 20 to 100 layers, each needing polishing in between. And again, water is kind of used within the part of making the wafers, not just making the chips themselves. But what's missing on this, bottom axis is ultra pure water. So there's more ultra pure water used, and I like to say that it's the single largest volume chemical in manufacturing, especially in semiconductor manufacturing. And so instead, on these graphs, all they say is, it's only listed in terms of wastewater, right? So I would argue it's important. It generates a lot of wastewater. The question is, how can we take that wastewater and make it back into clean water to be used in these processes? So what do they do today? Ultra pure water is made from city tap water for the most part. So the raw water is tap water. And you can look at either one of these little flow diagrams. They're pretty similar. I put them both up there because there's some slight differences, but pretty much they remove particles, they remove organics, unactivated carbon, they soften things, they do reverse osmosis, they do second reverse osmosis, then they do electrodialysis, UV sterilization, and more filters. And so they really need to make some of the cleanest water on Earth in terms of, ionic content. Typically the total organic carbon needs to be below 5 ppb and incredibly low particle counts, less than 1 per mil in this 50 to 100 nanometer size range. And as a consequence of this, the water recovery through this process is, at best 80%. So if they can come into this and reduce their reliance upon tap water, they can really, have an added, benefit here in terms of water savings potential. But there was this incident, and that's pretty well known in the semiconductor industry, and it was 25 years ago in the Northwest United States. This is published from Intel. And so it's a sketchy graph, but it's data. And on the y-axis is total organic carbon or urea. So they measured urea here. And again, their goal, was about 5 ppb. But you notice this spike, in April of 2001. And it goes up and it took time to come down. And that increased spike correlated with urea. And they did a lot of work. But here it turned out the urea was from a stormwater event and runoff from an agricultural field where they apply urea as one source of nitrogen. So this has really stuck in their minds that there are a few things that can make it through the ultra pure water system is the key takeaway here. And the problem is a little bit broader than just urea, but really any low molecular weight neutral molecule can pass through ultra pure water systems. However, they use a lot of those chemicals in making chips, lots of different alcohols, urea, TMAH, DMSO, and a lot of these. And so they're really worried about trying to treat wastewater from their fabs and make it back into tap water because they know that these low molecular weight organics have a high probability of making it through their existing ultra pure water systems. So what are the fabs doing in terms of wastewater reuse, even before they think about reuse or treatment before they think about reuse? So it depends upon their size, depends upon, their location. So it's kind of on the left, they just discharge to a sewer. They might need copper pretreatment, BOD removal, pH neutralization. Smaller fabs, not too much different than other industrial or CII sectors. I'll show a little bit more, but if they're going to do on-site treatment and reuse for non-potable applications, including not for making chips again, but usually involve a peroxide quench. So they use lots of hydrogen peroxide and organic peroxides, membrane bioreactors for COD and ammonia removal, softening, RO treatment, where the concentrate then goes to ion exchange, high pressure RO, zero liquid discharge, and the permeate for non-potable reuse. And I'll talk about that in a moment. And I think what we're trying to do is to go this next thing where you do that, and then you also use put in another treatment for these low molecular weight organics to supplement their tap water, where then the water would still go through maybe an ultra-pure water processing. So as I said, this would be a typical series of steps that's used at a lot of large fabs in the United States already. And it produces biological waste that goes to a landfill. In the end, crystallization, this goes to a landfill. So Intel here in Arizona has 2 crystallizers, an electric one, a gas one, and they bring off 5 to 10 truckloads of salt to a landfill every day. But the permeate here and the distillates are considered clean water that's used on site for cooling towers, gas scrubbers, and other applications. And so that's this kind of first level of reuse, is reusing that water for cooling towers and scrubbers. And it varies throughout the year, but maybe you have about 25% of the total wastewater that you produce can be used in these on-site things. So most of the water demand is processed water, and they don't use that for reuse applications currently. So the idea is to increase this pie where we can reuse water on site. So really what we're trying to do is to have cooling towers, continue those uses, but then use the ultra pure makeup water from this process instead of tap water. And the question is, what about these things in there? How do we treat them to create this new barrier? So now let's look, hopefully that's a good background on why we're interested in these low molecular weight. They, as I'll show in a minute, they will make it through a lot of existing reuse systems and through ultra-pure water systems. So who are the actors that we're talking about? These are very good, very representative compounds that actually occur in fab wastewaters that they use. They make it through membrane bioreactors. They're small. Their molecular weights are all under 100 grams per mole in terms of they have pretty high diffusivity rates and things like RO membranes. They're not acids, right? Or except for TMAH, maybe not bases. So they don't have any high selectivity necessarily through reverse osmosis, other than their diffusivity rates. And in terms of absorption, their octanol water partition coefficients are incredibly low, right? So they make it through, and things like activated carbon wouldn't do much to these. So you see some similar characteristics of them. There's not a lot of electron-rich bonds, and we'll talk a little bit more about potential treatments here. So as a consequence of their structure, adsorption, aeration aren't very good. So the focus, or the part of the toolbox that's maybe left if you don't modify your membranes, might be oxidation processes. And so why, or which of those chemicals do you target? So this graph on the right are 5 of these low molecular weight organics. The y-axis here is percent removal. The orange bars are through reverse osmosis. So urea, you get 30% rejection compared to isopropyl alcohol, where you get over 90% rejection. And you can see the other orange bars. And then the green bars are based on the rate constants, a few assumptions, but the ability to degrade them using typical advanced oxidation processes like hydrogen peroxide and UV. So you see that urea has a very low removal rate with the green bar, hydroxyl radicals, whereas some of the other ones, here, like methanol or formaldehyde, while they were not well removed by reverse osmosis, they are more susceptible to hydroxyl radical oxidation. So for a number of reasons, urea kind of emerges, not only because it occurred in an ag runoff and it's used in fabs, but it's also one of the more difficult ones to treat. So the typical concentrations after RO, based upon fabs and publications kind of around the world, are in this 10 to 100 parts per billion as carbon. Remember, the goal is usually less than 10, more like 5 part per billion of carbon. And so the alcohols and stuff are pretty easy to understand why they're used in a fab. Urea actually isn't widely used in a fab, but it is present in some of their organic polymer solutions as stabilizers and other products. So it's just like many other chemicals. It's hard to avoid, but it can be based upon kind of supply chains. But so you have a mix of these things, likely coming out of RO. So we looked, sorry, maybe I'll just reiterate. So initially we decided to focus on urea. That is, it occurs, it's the compound that would have the known risk of getting through ultrapure water. In ultrapure water systems do use vacuum UV and ozone, so they do generate hydroxyl radicals, but again, it can get through those systems. So for that reason, initially we focused on removing urea. Now there's some fabs around the world that have noticed this, and they haven't completely moved to reuse their wastewater yet. But one of the processes that they currently use is on RO permeate, they add sodium bromide and chlorine. And that produces hyperbromous acid or hyperbromide ion, which with long contact times of hours to tens of hours can degrade urea. So the way those processes work is if you enter kind of a chain decomposition around urea degradation, where you produce ammonia. The ammonia helps kind of regenerate this process. And here we focused on ozone because you can end up using the ammonia to kind of regenerate and drive this process, which happens a little bit slower if you use just chlorine. So here we focused on using, and the experiment here is a batch experiment where we added different amounts of sodium bromide, kind of a constant ozonation. And ozone alone, the gray symbols up top, you saw essentially, no removal. But when you add sodium bromide, you form hyperbromous acid, you kind of drive this reaction, and you get improved urea removal. Now, there's another data point on here, and we'll talk about this in a little bit, but we wanted to look at other ways to drive this process without adding sodium bromide to the system. And we used PMS, and I'll talk a little bit more about this, but this generates sulfate radicals as an alternative here. And the real reason is that while this process works well for urea, this ozone sodium bromide does not work well for things that do not contain nitrogen like urea. So if we are concerned about any of the other ones, we would need a different oxidation process. So we took this step back. We looked at urea and other representative low molecular weight organics on different rows. We looked at ozone, but we also looked at different radicals. The red values in here are data that us and our partners have filled in. But what we notice is that the reaction rate constants, that's what these are, in terms of second order rate constants, are pretty high for sulfate radicals. So that's that green intersecting box there. But it's also kind of fairly high for some of these other low molecular weight organics. So we decided to focus a little bit looking at these radicals. I'll talk about kind of ozonation experiments that we did with proxy monosulfate or PMS. In the presence of ozone, this generates sulfate radicals and hydroxyl radicals. So the blue line in here is ozonation now with ozone plus PMS, kind of relative to the ozone bromide, ozone alone. And later in the talk, I'll talk about the UV based processes. But for right now, thinking about this blue one. So it does degrade urea fairly well at steady state 5 milligram per liter ozone types of concentrations for reasonable reaction times. So we wanted to look at not just the removal of urea, but also the removal of total organic carbon or TOC. So again, on the left here, ozone alone or PMS alone had no change in TOC. You really, once you had ozone PMS, not only did you remove urea, but you mineralized the TOC. And that was matched on the right-hand side with the formation of nitrate. Again, these are ppb levels, but nitrate's not a problem. Nitrate is well, or even nitrite are well removed during, a conventional ultrapure water, purification system. So we're able to ozone, works in terms of sulfate radicals, hydroxyl radicals, and to lead to mineralization and inorganic byproducts. And as just a confirmation to be sure that we had both hydroxyl radicals and sulfate radicals, because sulfate radicals are good for some compounds, but for others of those low molecular weight, the hydroxyl radicals are important. So in this specific experiment, it was about 2/3 of the urea oxidation occurred via sulfate radicals and about 1/3 by hydroxyl radicals. So they are both there, was really the key point. So what's going on when you have this PMS is you activate it, you form sulfate radicals, and the key byproduct is sulfate, which is kind of not a problem. But what's very well known about sulfate radical chemistry is chloride is kind of the death of it. And that's really why it's not widely used. But we said, well, this is RO permeate. We shouldn't have much chloride. But it turns out that we do. So industrial semiconductor water, they use a lot of HCl and other salts that contain chloride. And the RO permeate can contain 25 to 75 milligrams per liter of chloride ion. So we wanted to understand what is the effect in this ultra pure water, essentially as a function of chloride to urea ratios. So here, this is still working at a pretty high urea concentration, 1,000 ppb. And what we see is that the black line is without chloride and even small amounts of chloride. So again, 35 milligrams per liter chloride is going to be 1 millimole, and you pretty much almost shut down the urea degradation. So we've done a number of tests with this, and essentially the way you can overcome this is by understanding what that chloride to urea ratio is, but you can put in just more PMS. So you can use more PMS to increase this, but it's going to really lead to less and less efficient degradation. So we learned a lot during the ozonation work, and then we wanted to look at other ways to make radicals that might not have all those same challenges. So we looked at vacuum UV based systems. So these are vacuum UV. They generate 254 nanometers, but then they also generate shorter wavelengths like 185 nanometer light. So in this experiment here, I'll show some more that have millijoule or doses on them. It's the same graph we looked at before. Here was that ozone PMS, and the purple line below it was a condition that we picked to give us similar urea removal. So clearly, here we use PDS or peroxy disulfate, that is slightly more photoactive. So that was the initial precursor that we used. And so we could vary the PDS concentration, and higher concentrations, 1 millimole PDS, and you get very, very rapid urea removal. On the right-hand side, you can see the effect of initial urea. So the blue line here is the most kind of, representative of full scale. This is around, 100 ppb of urea, or a little bit less as carbon. So, you can get rid of the urea fairly quickly. And so, again, we knew that chloride was going to have an effect. And so what we're looking at here in the black line is 1,000 ppb of urea with no sodium chloride. So we, in about 1 minute or about 2,500 millijoules per square centimeter, with a PMS, we degrade the urea and meet our TOC goal. However, in that system, if you have chloride, you can still get there, but it's going to require 5 to 10 times higher UV dose to get there. You can also add in more of the PMS. But then we looked at this kind of more realistic urea concentration, and maybe you need about 2 to 3 minutes or about 5 to 6,000 millijoules per square centimeter. So we're efficiently oxidizing urea even in a pretty high concentration for RO permeate of chloride. So we think this UV system works, and we've done a lot more work with different compounds. We've modeled all these systems. So this is just experimentally looking at urea degradation, nitrate formation, and we form a little bit of a cyanide as intermediates in here. But again, these are all at very low ppb levels, but if you continue them to go, you can degrade that as well. So how does this compare to other processes? And in this example, this is now beginning to look at some of the other low molecular weight organics as we kind of zoom back out here. And this is looking at IPA degradation. So sulfate radicals in red, more conventional UV, it's vacuum UV still, but with hydrogen peroxide. So it shows that we get better removal of IPA with PDS than we do with hydrogen peroxide. So the approach we're thinking of for urea will also degrade things like IPA. However, in real wastewaters, you don't have only just one of these. So we've been doing experiments, and this is just some of our models. These are kind of large models with 100+ reactions. And this example, we had all 7 of these compounds at an equal initial concentration of 1 micromole. This is with vacuum UV in a simulated batch. So over time or as increased dose, PDS concentrations go down. But we see that urea, the orange, is the slowest to degrade, but we see the evolution of formaldehyde and acetone as intermediates and byproducts of some of these other compounds. And so it actually emerges that acetone, if they're all present at initial concentrations, because it's an intermediate, actually is one of these key compounds to watch or to track. So we're going to be using online TOC instruments, but we'd want to be able to track some of these intermediates and products. So we're going to focus on acetone and urea. So that's a little bit of a story, about, 2 of these different processes. Again, on the left, we were looking at ozone. UV alone don't do anything. If you add ozone with sodium bromide, you can degrade urea. Ozone with PMS, you can degrade urea. Vacuum UV with PDS, you can degrade urea. And then on the right is looking at not just whether we removed urea, but really the TOC removal. And so the ozone sodium bromide doesn't work as efficiently in mineralizing everything. You end up with some of these, organic bromamine types of species in there. So to now come to the closing part of the talk, where are we going next with this? We've done a lot of batch work. We've dialed in terms of thinking about key doses, so combinations of batch and kinetic experiments. We have a really nice model that allows us to do everything. So now we're moving towards pilot testing. So our pilot testing is going to be at a full-scale fab starting late spring. This is a partnership through NAWI with Carollo Engineering. So we're going to take real fab wastewater. We have pilots that are being installed. Our part of this, for this part that I talked about today, is going to be taking the RO permeate and putting it through our trailer that has ozone, vacuum UV, and on the far bottom right, a real ultrapure water system. And so we'll kind of be able to follow that all the way through. Another group here at ASU, led by Taizang Tong, are going to focus on the brine aspects of this, which are a different challenge. But here we're going to focus on scaling up ozone, chlorine, and medium pressure and vacuum UV and some other UV technologies. So with that, I'd like to kind of summarize some of the key points. Advanced manufacturing is expanding, and most of those that need water need very high quality water. I talked about the semiconductor, but it's batteries, pharmaceuticals, kind of across the board, that these high value companies that we want to see growing in the US are going to need more and more ultra pure water. And there's opportunities to use and reuse their wastewater as makeup water, reducing their reliance on tap water. We think the biggest challenge of this is these low molecular weight organics that make it through RO on the reuse side as well as through the ultra pure water side. So we need to really develop some high technology readiness barriers that can be used to protect the high quality water. So any of the byproducts from this process that we're using, like nitrate, sulfate, are fine, even bromate, as long as we know that they could be removed in a conventional ultra pure water system. And again, our next step is scaling this up in a pilot system. So with that, again, I'd like to acknowledge my co-authors and funding. And I think we have time for questions, Tyler.
Yes. Thank you so much, Dr. Westerhoff, for that presentation. That was really great just to see like the background and motivation about like why we should care about water reuse for these specific industries. So yes, so if anyone has any questions, feel free to drop them in the Q&A box, and we can start answering those. We do have a couple. So curious about like when we talk about semiconductor manufacturing and the supply chain, um, could you talk a little bit about throughout the value chain what the most water intensive process or manufacturing like product is? Thinking about like wafer production versus like data centers, etc.
Yeah, let me go back to that slide because I thought this one, and this was actually a really nice, I gave the citation up in the upper right-hand corner, from kind of a policy review. That's where this, image is from. But when you think about the footprint of mining, right, it's combinations of silica, copper, rare earths, right, that they make into gases. And I'm trying to think if I've seen kind of a number for that entire supply chain. We focused on copper because there's copper mining here in Arizona, and the amount of copper the water that's used for the copper by the time you get to the chip is small for the amount of copper on the chip. So it's the manufacturing and packaging, part that is the more water intensive. Now, I'm not quite sure, and maybe other people know about copper or silica or some of the other things. But if you consider kind of, I guess, kind of like then downstream for data centers, kind of there, it's really clear that, if you think of scope 1, scope 2, scope 3 water in terms of, off-site for energy generation, on-site if you're doing evaporative cooling versus, the chips and things, that scope 3 water is really small in terms of the chips relative to scope 1 energy production. And then, if you're doing evaporative cooling, then, that's maybe, I think it's like 1/3 on-site and 2/3 energy production. But normally the chip part is less than about 5% of that whole supply chain for water footprint. But in terms of where the value is added, going from elemental copper or elemental silica, if you look at just a company like NVIDIA or something, right, that value is really coming because of this, advanced manufacturing capability. And then there's all different other reasons why we want these companies in terms of supply chains, within our country's borders and things like that. But yeah, it's a good question. But scope 3 water for data centers, the chips and everything else is generally considered small.
Gotcha. Great. Thank you. Um, okay. And then you mentioned Intel being one of the key manufacturers, especially in Arizona. Um, can you speak on like what their like perception of the water challenge is and their receptiveness to this kind of zero water discharge facilities and kind of like what their, from a manufacturer perspective, what their like priorities are when it comes to water.
Yeah, I mean, I can't speak for Intel, right?
Right, right.
But
Based on your
so my
experience.
experience and my discussions with Intel. So, Intel has two large fabs in the kind of Northwest and here in Arizona. They both do wastewater reuse. They both have reverse osmosis. They both have the capabilities to do zero liquid discharge. They don't necessarily use that all the time in the Northwest. Here in Arizona, they do zero liquid discharge all the time. They use the water for cooling water and cooling, evaporative cooling. So fabs use a lot of electricity. They generate a lot of heat. They have a lot of clean rooms that need a lot of HVAC cooling,
Mhm.
and they use it for scrubbers. In terms of their gas emissions, gas mitigation. So continuous flow, and they'll use some of it sometimes for humidity. But then they have a partnership with the city of Chandler. So they will reuse the RO treated water within kind of a jointly funded reuse complex. The individual drops of water may go different places, but in the end, anything that's not evaporated is essentially recharged into our regional aquifer. All RO, treated, before that for sure. So they have no real, discharge. So they are
Mm.
reusing it, entirely. Part of it, the reuse is, kind of regional indirect, recharge, if that helps.
Gotcha.
So they do really other cool things. If you're ever here in Arizona, they typically give tours. We have a NOWI meeting coming up, and Intel's giving a tour. They recover, let's see if I can get everything right, ammonium sulfate as a fertilizer. They recover calcium fluoride that's used in some other industrial processes. Most of the fabs will also separate, and they have processes on site to make sulfuric acid. So the sulfuric acid doesn't always go back into the chip manufacturing, but it goes back into like cooling tower water, other applications. So they'll make a lot of sulfuric acid on site.
Gotcha.
Yeah. So they try to reuse the water and the things in the water.
And and would you say that that is representative of kind of like the status quo in that industry, or is this more of like a
So no, I would say that it's cheaper usually to discharge to a sewer.
right?
So the larger the fab, the more viable, it becomes to do reuse. So Intel, for example, had, they're somewhere between 5, 8, 9 million gallons a day of super advanced treatment, both on the ultra pure water side and the wastewater side. They have a big team,
Mm.
uh, you know, um, that they never want to shut down the fab because of water is one way to think
Right.
about it. The other companies building and expanding here, while they might put in $100 billion for the fab, if you looked at those pictures I kind of showed for that one, the cooling systems are enormous in terms of cooling towers, and the water processing buildings are take them together, and it's larger than any one of the fabs. So these
Wow.
are large, expensive, capital expensive, and operating costs. But by doing it on site, you have a lot of ways to reuse the water, reuse elements in the water, kind of control, where the um, any potential pollutants might be going.
Gotcha. Okay, great. Thank you for that answer. And then digging into the processes that you were discussing and the piloting. So compared to biological treatment or other sort of treatment options for like urea and acetone and things like that, how much more expensive is the advanced oxidation?
Yeah. So the fabs, I'm talking about RO permeate, right?
Right.
So way upstream, they have the most common for these large ones would be membrane bioreactors already. So before the membrane bioreactor, they're going to have peroxide quenching with a catalase compound, and then they have to they biodegrade a very large amount of ammonia, TMAH, and these solvents, right? And so you know, they bring down the concentrations, a lot, even before it gets to reverse osmosis. So coming on to reverse osmosis, you're way below a milligram per liter, a few hundred parts per billion of these, and it's just from a primary substrate point of view, there's not much substrate left. So you could put in biofilters or things, but you know, on RO permeate, there's just you're not going to have enough growth to get to sub 5 part per
Mm.
billion, and then you're going to have to, worry about you know adding a primary carbon substrate to do it. So that's really why we've honed in on advanced oxidation processes. Using sorption, even activated carbon isn't really viable. All these compounds have super low, KOWs or very low adsorption potentials. And the same compounds in industrial wastewater like acetone are the same ones that are challenging for municipal, wastewater reuses. Orange County saw a pulse in TOC. It was associated with a commercial, industrial, institutional, I wouldn't say dumping, but disposal into their sewer that made it
Mm.
through all their biological processes too. So no, you couldn't get here without using biology upstream.
Right. Yeah, I remember seeing something about acetone being an issue with aquifer recharge.
Yep, right. In Orange
Um,
County and
yeah,
other places, if they've measured, if they even, the only way Orange County caught is that they had a high sensitivity online TOC detectors in their RO permeates. Yeah.
right. Okay, great.
Or
Good to
actually even after AOP there. Yeah.
gotcha. Cool. And then we also have a question about the pilot that you mentioned. Could you talk a little bit about what your measures of success are going to be for that, or like what specifically you're looking for?
Yeah. So, so the semiconductor, company that we're working with is kind of one end user. The other is NOWI, thinking about models to predict things. And so the thing that links them together is technoeconomics. So
Hmm.
we're really not quite sure. These are pretty high, UV doses when you're talking about 2 to 5 or 6,000 millijoules per square centimeter, but in the range of AOPs. And so our metrics of success is really going to figure out which is the lowest cost option among these. And we started doing full scale sampling, and there really is a mix of these low molecular weight organics. And so it's really dialing in how to understand how to get to that low TOC removal and knowing what they are. So we're trying to partner with some sensor companies who might be able to get to, low part per billion acetone levels, so we can both know what's there and the concentration. But the key, metrics are going to be driven largely by energy for the UV and generating the ozone. But then the other key one is technology readiness level, right? So if these are going in, ozone is a more mature technology compared to vacuum UV
Hmm.
at scale. And PMS or PDS are not really widely used as well. So I think it's going to be a combination of cost, technology readiness, and maybe the ability to build these out or scale these out as in modules as things like fabs build out over time. So I'm not sure, in terms of kilowatt hours per cubic meter, that's not necessarily the key point.
Hmm.
Here, it's the total cost, including the capital cost of
Right.
these systems.
Great. Okay. Thank you. And then you mentioned a low ppb kind of like target. Is that's based off the ultra pure water needs of the manufacturers?
Yeah. So yes, and so they can already achieve, sub 5 part per billion as carbon. And so the worst case would be if we brought in something that could not get removed at all through there, right? So
Hmm.
our initial target is 5 ppb as carbon. Yep.
Gotcha.
Yep.
Thank you. And then we have time for one more question.
Okay.
So great. Could you, towards the end of your presentation, you talked about the formation of different byproducts during the advanced oxidation process. Um, could you talk a little bit more about like any like byproducts that may form and how that impacts the quality of the water? Like maybe the byproducts that form and like don't continue like
Yep.
degrading. Are there any like harmful byproducts that you are looking at
Yeah.
for this
So
process?
again, people aren't drinking this water, right? So, or it's not going
Right.
into a river, it's not going into an aquifer. So we're really focused at, the things that would get removed still through subsequent ultra pure water processes, or maybe
Mhm.
you inject it somewhere after some part of that. So, we expect nitrate and nitrite to be there again at part per billion
Mhm.
levels. Sulfate will be there if we use PMS or PDS, and that'll be there at maybe the highest dose we've ever used is like 1 millimole. So it'd be like 1 millimole of sulfate, maybe. I think we showed in our modeling that acetone itself can be a byproduct of some of these. So acetone itself is a target of interest. And then some of, you have a lot of, um, urea, for example, at high concentrations, you can have some of these, cyanide-like compounds, emerging. So we definitely want to, focus on them. We've only been able to, we can currently, when we work at higher initial urea concentrations, we can quantify them using existing technology, but detect in terms of GC or LC mass spec. But we're really interested in using the model to understand what their concentrations are,
Mhm.
at the ppb level of carbon types of things. So we think we know what they are, and that's the nice thing is we're kind of starting with like pretty clean water, right?
Mhm.
So it's easy to think about these byproducts and then from a mass spec way actually prove they're there because again we're starting with pretty clean water to start with.
Gotcha. Okay, great.
Yeah.
Well, once again, thank you,
Great.
Dr. Westerhoff, for the presentation as well as the Q&A and the discussion. Really, really great to hear about all the work happening over where you're at. So for the folks on the call, we do have one final seminar for this, I guess, iteration. We will be hearing from Dr. Daniel Jamar in April on the end of the pipe, monitoring and controlling lead and other contaminants in tap water. As I said, this will be the final seminar in this sort of series, and then we'll be taking a brief hiatus over the summer before we hopefully return in the fall. So you can register for that on Current's website, and then be sure to stay tuned for future seminars as well. Again, thank you, Dr. Westerhoff. And yes, hope everyone has a great rest of their day.